So my name is Michael Kinsey. I'm a research fellow in the Fire Safety Engineering Group at the University of Greenwich. And I'm also one of the co-founders of the evacuation modelling portal, evacuation.net. Today I'm going to talk a bit about some of the work we've been doing with regards to lift evacuation modelling. Before I begin, I'd like to thank my co-authors, Professor Ed Gallian and Dr. Peter Lawrence, for their contributions. Now, as part of this work, we conducted a review of a number of incidences where people described how they interacted with lifts during real incidences. And one of these incidents was the World Trade Center 9/11 attacks. And here we can see three extracts from survivor accounts of people who interacted with lift systems during their evacuation. The first survivor thought that it was okay to use a lift because they still had power. The second survivor initially decided to use a lift, but decided that there were too many people waiting in the local lift area, so they decided to redirect to the stairs. The third survivor knew that she shouldn't really use a lift during an evacuation, but decided that she didn't want to walk down 78 floors wearing high heels, so she decided to use it anyway. These accounts, along with a number of other descriptions of how people interacted with lift systems during real evacuations, sort of exemplify the variety of factors which can influence people's decision as to whether to use a lift or use the stairs. Another thing we found quite interesting is the fact that a number of accounts describe how people initially made one decision, to use a lift, then decided to redirect to the stairs, and they adapted their decision making according to local conditions. And these are some of the factors we really wanted to start to think about in our modelling process. So, many buildings heavily rely on lifts during normal usage. Indeed, it's only with the use of lifts that such high-rise buildings or deep underground stations can be built. They provide an intermittent level of service, and they have very few physical requirements for using them compared to equivalent stairs or escalators. They're used to assist people travel long vertical distances, perhaps carrying items of luggage, and are heavily relied upon by disabled people. Typically, they service more floors than equivalent stairs or escalators. As such, they potentially provide an attractive means for use during evacuations. Indeed, there have been a number of actual incidences where lifts have been used to good effect to assist actual evacuations. Despite this, general use in building codes is restricted. There are some exceptions to this, and indeed there are a number of buildings, though they're more exception rather than the norm, which allow the use of lifts during certain evacuations. In terms of human factors associated with lift usage during evacuations, very little is understood, and there have only been a small number of studies looking at this. There is a lack of understanding regarding this behaviour. In terms of computer modelling, and because we have a lack of understanding regarding the human factors, most models either assume optimal agent behaviour, or they require the user of the model to specify how agents are going to behave. As such, most of the studies which we've reviewed that look at a lift evacuation typically are used to demonstrate the potential benefits of using lifts during evacuations rather than predict what is actually going to happen. So considering this, we identified three key research aims that we wanted to address in our work. The first was to collect human factors data and try to understand how people behave on and around lifts during evacuation. We also wanted to develop a model to represent not only the lift, but how people interact with the lift within an evacuation. And then finally, we wanted to use the model to explore how different lift strategies and how different human factors may influence an evacuation. Now, I've actually previously presented our work at other conferences related to human factors and model development, and I'm going to only give a brief overview of these areas before I focus on looking at our modelling work and some of the results we've got out from it. So for the data we've collected, we conducted an online survey posing a series of hypothetical evacuation scenarios and asking participants how they would react with regards to using lifts or stairs. Again, we've presented this work previously, so I'm happy to talk about this after if anyone wants to know more details. Key findings from this work were that despite being told that it was safe to use a lift during an evacuation, only about 50% of people would even consider using a lift. So there's 50% who wouldn't even consider using a lift straight off the bat. Our results suggest that increased familiarity appears to decrease people's likelihood of using a lift, and this may be because people are more familiar with the alternatives within a building. As found in some other studies, the higher people are located in a building, the greater chance they would have of using a lift during an evacuation, and also the greater tolerance they would have to waiting in higher levels of congestion for longer periods of time. The results suggest that age, gender and BMI don't appear to influence people's consideration to use a lift. However, it must be kept in mind this was an online survey, so participants' physical characteristics may have had a diminished effect upon the results. Having said this, the results do suggest that country of origin does appear to have an influence on people's consideration to use a lift, with those participants from the US and Germany being considerably more likely to use a lift compared to those from China and the UK. So, we've developed a model within Building Exodus to represent the lift system. This can represent various physical components of the lift, also various kinematic components of the lift, and also some delay times associated with lift usage. There's also a lift car control mechanism, which allows a user to specify how a lift will behave within a given scenario, and it allows a user to define how they want the lifts or what strategies they can use within a simulation. Now, using the data we collected from the online survey, we use this to instruct the development of a lift agent model to interact with our lift model within Building Exodus. And essentially this relates to the decisions agents make of whether they're going to use a lift or use the stairs at different points within a simulation. So initially, agents decide whether to use a lift or stair. And again, this is based on the data we collected. So they have a probability, given the floor they're on, of using a lift or a stair. If they decide to use a lift, when they enter into the lift waiting area, the area close by the lift, they'll then assess the levels of congestion. And if the levels of congestion are too high, the agent will redirect to the stairs. Again, this is based on the data we've collected in our online survey. Agents will wait a predefined amount of time, a maximum predefined amount of time. If the lift hasn't serviced their floor or they haven't boarded a lift before that time is expired, they will redirect to the stairs. And there's also a separate algorithm to decide which stairs they use and also which lift they use in making their selection. Again, this model is described in a lot more detail in previous work and also my thesis, which I'll be happy to share with anyone who wants it after. Now, we've used this model to construct a series of 11 lift evacuation strategies, and each scenario explored using lifts in different ways to evacuate a building. Each strategy was run once using our initial lift agent model, and this is when we forced all the agents to use a lift, and we said they're not going to exhibit that adaptive behaviour. Everyone that can use a lift does use a lift. So in these cases, we're interested in exploring the impact of the lift strategy upon the evacuation. We're only interested in the lift strategy. We've also run each scenario using an enhanced agent model, where we've incorporated data from our online survey. And here we've given agents the ability to adapt their behaviour and to make a decision as to whether they are going to use a lift or use the stairs. And this is typically based on the floor they're on. So what I'm going to do, I'm going to focus on the results of our enhanced lift agent model, which is intended to explore how lift human factors may influence different lift evacuation strategies. At the end, I'm going to briefly give a comparison between these results to our initial agent model to suggest how the potential impact it may have to include human factors in a model. The demonstration building was exactly the same building for all cases, and this had 50 floors, just under 8,000 participants, 4 lift banks, and each lift bank contained 8 lifts. Each lift bank had an associated stairwell associated with it. So here you can see that the stairwells were located approximately in close proximity to each lift bank. And this is a floor plan of one of the floors in the building. And there's a 3D output here. So here we have a video of scenario 11, just to give you a feel for what a simulation may look like. This is of the initial lift agent model. I've turned off the walls so you can more clearly see the agents and the lifts themselves. What you can see here is the grey columns, they're the lifts, and what we've done, we've coloured agents according to which sky lobby they use. And in this case, agents will walk down the stairs to a lift sky lobby, they'll board a lift, they'll go down to the ground floor, and you can see them discharging on the ground floor from the lift and then going to their exits in the left-hand plane here. So this is an example of the type of simulations we've run. So the first scenario looked at using stairs only. We didn't use lifts at all. And this was intended to see how the building could perhaps typically be evacuated using perhaps the current building code. And this is going to be used as our base case to compare with our other lift scenarios. The next 4 scenarios gradually increased the number of available lifts, and agents were told, well, you have the option to use a lift or stairs. They don't have to use it, but they have the option to. And we're seeing what influence the frequency of lifts have upon the evacuation results. So in these scenarios, the stair users were the last to evacuate in all scenarios. Remember, agents had the choice to use the lift on all floors. There was a marginal decrease in total evacuation time compared to our stair-only case, between 9.7 to 18.9%. In all of these cases, lifts were heavily underutilised. And you can probably see this in this chart here, which, if you look at the bars which are white, this is the number of agents which redirected from the lift waiting areas because their wait time expired. In this strategy, all the lifts would service the upper floors, evacuate people from there, and then gradually work their way down the building in a top-down strategy. And these strategies are not very appropriate for the overall building because people not on the upper floors are not prepared to wait long periods of time to actually use the lift. If we break down these graphs according to floor number, so here we can see the proportion of agents on a given floor that used the stair, that redirected from the lift waiting areas due to wait time, that actually used the lift or redirected because the congestion levels were too high. What you can see here is that as the number of lifts increases, the areas of black in these charts gets bigger, and that's as expected. The more lifts you have, the more people are going to use them. Another interesting thing to note is the areas of white. On the upper floors, you can see that very few people redirected due to wait time. And this is because lifts service those areas first. So very few people redirected due to wait time. As you get lower and lower in the building, more and more agents begin to redirect due to wait time because they're not prepared to wait long periods of time. As you approach the lower floors, less people redirect due to wait time. And this is simply because there are less people who are actually considered using a lift on the lower floors. In terms of the time people actually waited for lifts, we can break this down according to the lift wait time for lift users and also lift wait time of those that didn't use the lift but initially chose to have a look. The lift user average lift wait time ranged between 3.8 minutes to 6.3 minutes. And again, as the number of lifts increases, the lift wait time approximately decreases. So people are having to wait less time when you use more lifts, as expected. But overall, the results suggest that evacuating the entire building in a top-down evacuation strategy is just not very efficient, because people on the middle and lower floors are just not prepared to wait long periods of time. So the remaining scenarios looked at using combinations of both lifts and stairs to evacuate the building. And we use the concept of sky lobbies, where people could walk down the stairs, then have the choice to use a lift and go down to the ground floor, and also shuttle zones, whereby the building was vertically segregated according to different floor ranges, and then lift banks would service a given floor range. So scenario 6, we told everybody in the bottom half of the building to use the stairs. Everybody in the upper half of the building had the option to use the lift to evacuate down to the ground floor. Now, similarly, in scenario 5, we said everyone could use the lift, and what we noticed for agents in the bottom half of the building, many agents initially decided to go and use a lift, but then decided, I'm not going to wait, I'm going to go to the stairwells. Now, this initial task staggered their arrival to the stairwells in the lower half of the building, and this meant that people in the upper half of the building could filter down into the lower half of the building much quicker. So the time to clear the upper half of the building was quite quick in our scenario 5. Conversely, in this scenario 6, all agents are told you have to go to the stairs straight away. Now, this meant that the levels of congestion in the stairwell built up much quicker. As a consequence, people in the top half of the building couldn't filter down so quickly into the bottom half. So we noticed that the time to clear the top half of the building in this case actually took 2 minutes longer. If we look at scenario 7, it's very similar, except instead of taking people in the top half of the building down to the ground floor, we take people down to the middle floor, and then they have to use the stairs. Now, as expected, this result produced very similar overall evacuation times compared to our stair-only case. And this is because, effectively, everybody has to use the stairs at some point. And indeed, the evacuation rate was comparable to our stair-only case. Scenario 8, we said everybody in the top half of the building could walk down the stairs to a sky lobby, and then they had the option to use a lift to take them down to the ground, or they could carry on going on the stairs. Now this produced our second shortest total evacuation time, which was 30.6% less compared to our stair-only case. And indeed, the majority of agents which considered using a lift actually used a lift in the scenario. And this is for two reasons. The first reason is because people initially used the stairs to go before going to the lift sky lobby, this staggered their arrival to the lift waiting areas. So the levels of congestion didn't build up as quickly. So less people redirected from those areas because of the high levels of congestion. Secondly, the lifts only had to service the ground floor and the sky lobby floor. As such, people didn't have to wait a long period of time to board a lift. So less people redirected due to wait time. In scenario 9, we employed the concept of shuttle zones, and we segregated the building into 4 zones. And each of the 4 lift banks serviced a separate zone, a vertical zone. Now, the initial evacuation efficiency of this case was very good, and this was because agents initially in the middle to lower floors were evacuated first, because the lifts had to travel a short distance. So these people got evacuated quick, and we get quite a steep gradient on our evacuation curve. However, towards the end of the evacuation, the efficiency decreases quite a lot. And this is because people on the upper part of the building, it takes longer for them to evacuate because the lifts have to travel further. So you notice this arching effect on the evacuation curve. Scenario 10, we decided, well, we'd do exactly the same thing, except people on the bottom 10 floors are going to be forced to use the stairs to see if we can't gain some improvement in efficiency. Now, because few agents actually even considered using a lift in the bottom 10 floors, this had very little influence compared to our scenario 9. So the results are very, very similar. There's only a marginal decrease in overall evacuation time. Scenario 11 was very similar to scenario 8, except we employed the concept of a sky lobby, 4 sky lobbies instead of a single sky lobby. And each bank of lifts serviced a separate sky lobby. This produced the shortest total evacuation time of all scenarios, which was 33.1% less than our stair-only case. And this was for much the same reason as scenario 8. The majority of agents which considered using a lift in this scenario actually used a lift because of the decreases in the levels of congestion and the decreases in the overall wait times for the lift. Again, if we look at the proportion of agents which performed a given action on and around the lifts, if we look at scenarios 8 and 11 here, these are our sky lobby cases, you can see this big area of black, and that means that the lifts were more fully utilised within the scenarios, and there's very small areas of white in these graphs. If you look at scenarios 9 and 10, this is our shuttle zone scenarios, what you can see is that agents initially higher up in the shuttle zone had a greater chance of using a lift. And this is expected because the lifts service the upper parts of the shuttle zones first and work their way down. So as you're initially located lower and lower in a shuttle zone, you have more chance of redirecting due to wait time. So as I've mentioned, we've previously conducted exactly the same evacuation scenarios, but using our initial agent model. And in these cases, we forced everyone to use a lift. And here we're going to just compare 2 factors here with our enhanced agent model where they exhibited adaptive behaviour. If we look at the shortest total evacuation time for both models and compare it to the time it took for the stair-only case, we managed to reduce total evacuation times by 50% using our initial agent model. And this is whereby it was perhaps unrealistic behaviour, but we managed to decrease times by 50%. Using the enhanced agent model, whereby we've perhaps got more realistic behaviour, this reduces to 33%. If we look at the time to clear the upper half of the building, or the shortest time to clear the top half of the building, and again compare it to our stair-only case, using the initial agent model, we managed the best performance we had was reducing this time by 39%. However, this managed to improve using our enhanced agent model by 46%. What we think these results highlight, and indeed there's a number of other analysis we've done, is that the inclusion of human factors in your lift evacuation model can have both positive and negative impacts upon your results. And this is dependent on the life safety priorities you have for your scenario. For example, in this case, if total evacuation time is most important, then the inclusion of the human factors we've represented actually has a negative impact upon your results. However, if clearing the upper half of the building is most important, then the inclusion of the human factors actually improved your results. So it's something worth considering, and we think it's important to consider both the lift strategy and human factors combined rather than just one or the other. So to conclude, the determination of a suitable lift evacuation strategy is dependent not only on the number of lifts available and the nature of the particular emergency scenario, but also on the life safety priorities you have. We've demonstrated that human factors can potentially decrease the efficiency of a lift evacuation strategy in terms of overall evacuation times. The extent of this influence is dependent on the lift strategy employed. We've identified some lift strategies which are found to be less susceptible to the inefficiencies caused by human factors. And it's hoped the current studies highlighted the need to represent realistic human factors within lift evacuation models. Just to finish off, there are of course a number of limitations and suggestions for future work. These can be broadly categorised into our data, our model and our simulations. In terms of data collection, we obviously need actual and experimental data. There's very little data and we've collected an online survey and there are a number of limitations to do with that. We also need to think about how the data fits in with a general theory of human behaviour. In terms of modelling, the model is not entirely empirically based. We've collected some data, but we've been required to make assumptions about certain types of behaviour. For example, how people wait for a lift and where they stand and things like that. In terms of simulations, when someone selects to use a lift or a stair, we've assumed that they evenly distribute between the available lifts and stairs. So there's an even usage of devices per floor. This may not necessarily be true. We haven't explored the influence of uneven core usage and what influence this may have upon an evacuation. We also haven't explored the applicability of the results to different building layouts and different building heights. So all of these factors should really be considered when interpreting the results, and hopefully it will give some people ideas for guiding future research. Thank you.
Very interesting presentation. Look forward to some discussion when we get to that section in a little bit.